first three because I only have, how much time do I have? Like, we're gonna run out of time. I'm gonna talk about the first three. But if you want to talk about the other two, we can talk about it maybe during the question and answers. The first is we have to improve population health. And second, ensure reliable research results, which sounds like not such an ambitious thing because we do a lot of reliable research already, but let me, I'm hopefully convince you otherwise that we need to address this problem. And then third, we need to have a culture of science where big advances are possible, right? And again, you're saying to yourself, we already have that, but I'm gonna try to convince you that we can do better. Okay, so first, let me talk about improving population health. Think about the MAHA movement. Like those of you who've like been paying attention for the last year and some, a lot of the discussion around the MAHA movement have been very narrowly focused on a set of few topics, and it, in a sense, has become politicized. But it's not actually a political desire. The MAHA movement is a desire for every single by every single American to see that that their health gets better, that the products of science, the investments that we make in science actually translate over to solving the health problems that people have, and they are considerable. The MAHA movement exists. Let me show you a graph that explains why the MAHA movement exists. Right, so this is life expectancy in the United States from 2001 to 2024. Ignore for a second the attention-grabbing picture, the collapse on the right. Everyone knows why that happened. What I want you to focus your attention on is the flat line in the middle. From 2010 to 2019, there was no improvement in life expectancy in this country. Now, I was a researcher in demography, studying population health in the 2000s, early 2000s, and the big debate back then was whether the increasing life expectancy was going to translate over into a compression of morbidity. The idea being that, well, you have to die sometime, but maybe we can have our healthcare system as we get old, as we get longer and longer lived, to make it so that we spend less and less time disabled, in a disabled state. Longer and longer healthy life expectancy, shorter and shorter unhealthy life expectancy. That was the debate in the 2000s. We took it for granted that the life expectancy increases that you see on the left side of that graph will continue forever. The flatlining of life expectancy from 2010 on was entirely unexpected, at least by me and I think many people who study demography. And in fact, it's not shared by our rich country neighbors. But if you look, I should have brought the graphs, but like if you look at the data from Sweden, if you look at the data from Germany, you look at the data from France, you look at the data from Australia, what you'll see is continued increase in life expectancy after 2010. Unique among rich countries, the United States has seen a flatlining of life expectancy. And again, just ignore for a second the collapse in life expectancy on the right. But I want you to understand I want you to put the MAHA movement in this context. We've had so many incredible advances in science, so many things that appear to me as I studied medicine and in the early 90s that looked to me like magic. Right? We can cure sickle cell anemia. Something that was unimaginable. We can do gene editing of rare conditions and make children have healthy lives as a result of it. But for the typical American, all of these advances have not translated over to longer, better lives. And the chronic disease crisis is well known, right? So huge increases in diabetes, type 2 diabetes, huge increases in obesity rates. We have had huge improvements, thanks in part to Mount Sinai and other institutions like yours, in improvements in cancer mortality, but cancer incidence continues to go up. Now, there's debates over what exactly that means. It could just be better screening, and so lots of other things could be going into it. But the point is that we have not solved cancer, despite decades of a war on cancer. We have huge problems in the health of most of the country, and that's during a period when the biomedical institutions in this country have been tremendously successful in scientific advances. So the MAHA movement is a cry for help. And it's a cry for help to the scientific institutions of this country, the biomedical science and scientific institutions of this country. How can we translate these fundamental ideas, of which I'm tremendously proud as an NIH director, something that is fundamental to what the NIH is about? How can we translate it over to better lives for people? The collapse. The NIH's role, the very mission of the NIH, is to find ways to prevent, treat, and chronic diseases. Actually, the specific mission is to support research that improves health and extends life. Right? That's the specific mission of the NIH. And so to me, that is the fundamental, the most important reason, the reform I want to make to the NIH. I want the work of the NIH to translate into better health for Americans. And I suspect that every single person in the room that does science for a living feels the same exact way. In that sense, we are all MAHA. Right? We all want to make America healthy again through the work that we do. It's an opportunity for collaboration rather than the sort of conflict I think I've seen the last year as NIH director between sort of parts of the scientific community and the MAHA movement. Instead, we should be looking for alliances because we share the same mission. Okay, I'll talk. There's going to be, I think, an hour long. So I've left a lot of time for conversation and questions. We have 40 minutes. Oh my God. Okay, I better hurry then. Okay, so the second thing is ensure reliable results. Now let me justify this. All right, so. When I was in medical school, and I'd love to know if those of you had a similar experience. When I was in medical school, one of my very favorite professors looked at me and said, Jay, this is like 2 years into studying the prep cycle, where like I've memorized it 15 times, right? So, Jay, half of what we're teaching you is false. Anyone have that conversation with the professor? And then, well, what did you do? You said you looked at the professor and said, well, which half? I was taught in medical school that the cause of ulcers was stress. Peptic ulcers was stress, right? And the way you treat it is you tell people to reduce stress in their life. Well, it's hard to imagine a more stressful thing than a doctor telling you to reduce stress in your life, but that's another thing, right? So, and now we know that that a major cause of ulcers is actually a bacteria, right? That was a major advance since I was in medical school, right? It's normal and expected that scientific research will invalidate previous scientific knowledge on things. That is a perfectly reasonable thing to happen. It's normal and expected that half of what we know, will ex post turn out to be incorrect because we will advance our knowledge, right? That's fine. But the problem is even worse than that. It's not just simply that science that there's advances in science that overturn previous knowledge. It's that large chunks of the published biomedical literature are simply just unreliable, in the sense that when independent research teams try to replicate or reproduce the same result, they find a different answer. A colleague of mine, a very famous scientist named John Ioannidis at Stanford University, wrote a paper, which you see there on the left, with the ridiculously audacious title of "Why Most Published Research Findings Are False." I'm just curious who's read or seen this paper before. It's one of the most famous papers and most highly cited papers in all of science. I read it in 2005, and it hit me like a thunderbolt. And because if you look at the reasoning behind the paper, there's a little bit of Bayesian math. It's not that complicated sort of mathematically. But the fundamental issue that John is addressing is that science is hard. It is very, very difficult to advance our knowledge about the way that the physical world works. And then B, that the sort of standards that we scientists hold ourselves up to when we're deciding whether a scientific idea is true or false are too low. Science advances primarily because other people check our work. I fully anticipate there's work that I published where other people will look at it and say, "Oh, Jay, you got it wrong." And yet, we built a culture in science where that kind of replication is seen as a threat rather than what it actually is, which is an honor, right? So if someone subjects my work to replication, that means my ideas are important enough to be subject to replication. It's actually a good thing. And yet we have created a culture of science where we look over our shoulders and worry that someone's gonna come after us, try to get our papers retracted or whatnot, rather than a culture of science where we hold ourselves to tremendously high standards of proof. And that standard of proof being, well, I did a scientific idea, I checked it and tried it out. Some other folks try it out, they find the same thing, they try a different angle at the same thing, they find similar answers. That kind of consilience is what determines and gives us confidence in scientific ideas, rather than, I published in Nature, or I published in Cell or something. That's too low a standard of proof. Peer review also is too low a standard of proof. It's necessary, important, but it's too low a standard of proof for deciding whether scientific ideas are true or false. There's this, look at this, is there a reproducibility crisis? That was a paper in 2015, I think it was. 2016 where the answer to that question is yes. Since John's seminal paper on this topic, there have been a number of large-scale efforts to assess the reliability of the published biomedical literature. Right, so here's one. Huge reproducibility project fails to validate dozens of biomedical studies. You can go look at the paper up yourself just to see if I'm not cherry picking. You can replicate this, in other words. But here's the bottom line. Only 21% of the papers examined by this large-scale effort to assess this is in basic science, of the experiments were replicable. The effect size reported in the published biomedical literature was on average 60% larger in the original papers than the experimental follow-ups. This is actually a common finding in the reproducibility research, that when other people replicate the studies, the original study always overstates the effect size relative to what the replication results found. Only 21%. In field after field after field, we've seen these replication crises. Right, in psychological, okay, this one's really interesting because there's all kinds of fun results in psychology, which I have grown up with and loved. The marshmallow experiment. Anyone know that experiment? I love that experiment so much. It's so good. And if you ever have 2 free minutes, go look up on YouTube these little kids subject to the marshmallow experiment. Well, here's what they do. These are researchers at Stanford in the 60s, right? What they do, they got little kids, 3, 4, 5 years old. They sat them down in a little room and put a little plate on in front of them with a single marshmallow, right? And they told them, if you don't eat this marshmallow over the next 5 minutes, we'll give you 5 marshmallows or something, right? And then they leave the room, and they videotape the kids squirming in front of the marshmallow. There's one little this YouTube video is incredible. Please go watch it. The kids are squirming, and he's licking the marshmallow from the side, doesn't actually touch it. And then it turns out that the kids, this was reported in this original study, that the kids that didn't eat the marshmallow in those 5 minutes, 20, 30, 40 years later, do better in life. More likely to have a job, more likely to graduate from high school, all these I love that result so much. I desperately want it to be true. But then there was a recent paper questioning whether it's true. And I desperately wanted to fight. My instinct was that obviously this replication result is wrong, but there's more nuances to the story. The replication is an opportunity for us to understand the science better. Is it wrong? Is it right? I mean, I still want to believe it's true because of the cute videos, but I also even more want desperately to know whether it's true. Is the psychological ability to be patient built into us from childhood on, or is it something we can learn? That's a really important question, right? And yet, large parts of the psychological sciences do not replicate, right? So this is a paper that was published in Science from the Open Science Collaboration, assessing whether the replication they looked at 100 experiments published in papers in 3 high-ranking journals in psychology, and they would assess, and here's the bottom line, assessing whether the replication of the original experiment yielded the same result according to several criteria. They find that about 1/3 to 1/2 of the original findings were observed in the replication study. Like 1/3 of the time, the scientific results in the top journals replicated in psychological sciences. Okay, you're sitting there, and Eric is not going to agree with this, but like everyone else as well, is like, okay, it's just psychology. I mean, who cares? Cancer biology, surely cancer biology replicates, right? Here's a paper in Cancer Biology, published in 2021 by the Center for Open Science, Reproducibility in Cancer Biology, Challenges for Assessing Replicability of Preclinical Cancer Biology. The Reproducibility Project looked at the effect sizes and conducted power analyses that were publicly accessible for just 4 of 193 experiments. In other words, they couldn't, in 189 times out of 193 papers that they looked at in cancer biology, they couldn't figure out the statistics from the published results. They couldn't figure out statistical power calculations. The data needed to compute even just the effect sizes, to replicate the effect sizes, were not available in the published scientific literature. This actually gets worse. Like many of them, when they actually try to check the experiments, they don't replicate, even in cancer biology. What happens is that drug companies, when they're making decisions about whether to invest tens of millions of dollars in phase 3 trials, they don't trust the scientific literature. So they will conduct their own private replication efforts, so that the drug companies know which parts of the scientific literature replicate, but scientists at large do not. Doctors at large do not. Patients at large do not. So again, this very depressing article by Prince and his colleagues. Believe it or not, how much can we rely on published data on potential drug targets? At Bayer Healthcare in Germany, only about 25% of published preclinical studies could be validated to the point which projects could continue. 3 and 4 don't replicate. And it matters. That means 3/4 of the projects they have, they don't have enough confidence in the published biomedical literature to invest in. What if half of those are true? That means those are huge opportunities that are missed, right? Half of those 3/4 are true, right? Those are real. If we had a reliable scientific literature that they could rely on for making decisions, think how much more. Now, I say this in the context of understanding that we have had tremendous advances in biomedicine. I say this as a way to improve what we have, right? And I'm not trying to say this as a criticism to say let's give up. This is what it is a spur for better to do better. Let me tell you my sort of approach to this as an NIH director. There's sort of like 3 kinds of things I'd like to see done that I think potentially could change the culture of replication. First, we have to actually support replication, right? Those of you in the room who've had NIH funding in your career, how many have been funded to do replication work? 1. God bless you. Have you ever who has in their file drawer a failed research project that they could not get published anywhere? Every single scientist you know I've ever talked to has that. Why is that? Vast chunks of science are just essentially sitting in the heads of individual scientists rather than not shared with the community at large. We don't share our failures with each other. We don't share our replication work with each other. We don't support it. That's going to change. Like, I'm not saying I'm going to fund 3/4 of the portfolio as replication. That would be crazy. But what I am saying is that I want more Johnny and Edie's around. I want people who do replication work in clever ways to get our level support. And the challenge I have to university administrators is promote them. Give them the same honor that people who do fundamental discoveries in biology get, because they are a fundamental part of our scientific community. And they make the scientific community better by giving us confidence that the results of the published literature are true. So we're going to start having opportunities for scientists to do replication work. Part of that means that I want the scientific community to decide which results should be subject to replication. It shouldn't be the government saying this result should be replicated and this result. It should be the scientific community should decide this. And to do that, that means the scientific community is going to have a say. It's going to be peer reviewed as a central component of this. So that'll happen. The second thing is we need to change our standards for deciding when things are true, right? So if you've ever done a PubMed search, you pull up the results of the paper. You look at the paper and a whole bunch of buttons like citations, papers that it cites, the full text or whatever. All these buttons. we should have a button that says replication, that gives a summary